1.51, the mean value theorem for integrals. Now let f be a continuous function on the closed interval ab. The fact that it's closed is very, very important. And then the theorem states then there exists a point inside AB, it could be the endpoints, where the integration of fx from a to b is equal to b minus a times f of that particular point. Again, this point can be the endpoint. That makes the mean value theorem for integrals slightly different from the regular mean value theorem, because the regular one states that x has to be inside. Which means, well, it doesn't have to be, but x is strictly inside. You can nail it down to be inside the interval and not just on the endpoints, which means that theorem is more powerful than this one, because this one doesn't exclude the endpoints. Now, to prove this theorem, let's here's what we will do it. Okay, the proof states that we'll pick 2 points. M is the minimum, small m is the minimum of f on AB. And then big M is the maximum of f on AB. So then if you draw the graph out of this thing, you have, say, this is A, and this is B, and f goes around in there somewhere. And then the absolute highest point, say right here, is that's the big M, and the lower point is small m. And being that f is continuous on the closed interval, you know that it has to start somewhere, and it's continuous, can't break, and it has to end at a definite point. So no matter where it is, eventually you will be able to find the absolute maximum and absolute minimum of f. Now that is actually a theorem we will prove later, but being that it's intuitively obvious, we will simply quote it now. We'll prove it a bit later, as this actually does happen. It's not just an intuitive claim. So anyway, we have m and m like that, and then by the definition of the integral, a definite integral's definition goes like this. Summation of f xi delta xi, okay, when I goes from 1 to n, is this is the definition of that as n goes to infinity. So then this, what is that? That is, we will claim that it is bigger than or equal to, if we replace small m with this value, then we can plug it up and say this is delta xi. Again, I goes from 1 to n. Because now we simply replace f as the smallest value, which you can see is intuitively makes sense, because this is roughly the area under the curve here, and that is the least it can be. Okay, we multiply by the small value because the summation of this is just a from a to b, all the little chunks that we divided. Similarly, this value is less than or equal to big M summation of delta of x I. Okay, and then next, because this we will continue calculating what is the summation of this thing. The summation of delta I to n of delta xi is simply equal to b minus a. That's by definition. Okay, that's what this stuff is. So then we have, and so let n go to infinity. We will have m times b minus a will be less than or equal to this thing when n goes to infinity is the definition of this, the definite integral of fx dx, which is less than or equal to the big M times b minus a. Okay, now writing it a different way, then we get simply m is dividing everything over b minus a. Fx dx is going to be less than or equal to big M. All right, now we will call this value right here, we'll give it a value and we'll call it mu. Now here's the deal. Now you notice that mu is between m and m. Okay, so since f is continuous on AB, this is very important. Again, the continuity matters greatly here. Because f is continuous on the closed interval AB, and m and m are the maximum and the min, then f must hit mu at some value. That is, because mu is between the f's maximum and minimum, there must be some value where x in AB, where fx equals to mu. In other words, if mu is in here somewhere, okay, let's say this is mu, then there must be some value in there, at least, where fx equal to mu. Again, this is an intuitive argument of the continuous function that seems kind of obvious, but we will prove this as a formal theorem later. For now, we will simply accept it. That because the minimum and maximum of f, the absolute minimum and maximum, then f must hit every value in between those things, including mu, at some point x. Okay, that is on AB, which means that so then what we get is, so f of x equal to, for some x, equal to this expression right here, 1 over b minus a integrated from a to b fx dx. And that means, and this equation is exactly the same as this one. So it just means that we have found the x that is on the closed interval, which is the average of the definite integral of f.